event on electrification of special uses, labs, and manufacturings. I'm Helen Self, City of Sacramento Community Development Department and staff lead for the electrification ordinance. City staff have received direction from City Council to begin the process of adopting an ordinance that will require new construction to be all electric and will also include requirements for and incentives for the electrification of vehicle infrastructure. The city is hosting the topic-focused webinar outreach series to support the electrification ordinance. These are intended to be educational, but also to provide an opportunity for staff to learn from the various stakeholder groups. In order to leave time for us to focus on today's topic, I'll be giving a very quick overview of the proposed ordinance schedule and draft effective dates. Our key presenter is Stet Sanborn with the Smith Group, and then Stephen Oliver will give an overview of SMUD incentives. Electrification reduces greenhouse gas emissions and has significant public health benefits. If you would like more information about the city's rationale for the electrification ordinance, background on how we got here, or general information about electrification, please visit the city's project webpage. The first two components, go to the project webpage and look for a previous webinar called Electrification 101. The first two components of the proposed electrification ordinance will be local amendments to the California Building Standards Code that would live in Title 15 Buildings and Construction Code of Sacramento City Code. So the first component is to require all new low-rise buildings of 3 stories or less to be constructed as all electric by 2023 and all buildings by 2026. And this is provided that buildings of 4 stories and up are shown to be cost-effective and feasible. The second component is to require 20% electric vehicle capable charging spaces and at least 1 installed operational level 2 EV charger to be constructed in new multi-unit residential and non-residential development of 3 stories or less, 2023, and all buildings by 2026. And then the third component is to amend Title 17 of City Code, and this is the Planning and Development Code, to support EV charging with incentive that will be effective in 2021. This incentive for EV charging stations is to allow the substitution of 1 EV charging station for every 2 spaces, or 10% of required on-site parking spaces, whichever is greater. The potential ordinance adoption timeline presented here includes ongoing outreach with a focus on November through January. We anticipate possibly taking the ordinance to the Planning and Design Commission in January and to Law and Legislation Committee in February, and finally to City Council for adoption in March. The draft effective dates are for 1 to 3 stories, January 1, 2023, 4 stories or more, January 1, 2026, and for the EV parking incentives, 30 days from adoption. It's anticipated that complete building permit applications, including payment of all required fees, filed with and accepted by the city's building division prior to the effective date of January 1st, 2023, or January 1st, 2026, respectively, would not be subject to the electrification requirements. The proposed effective dates are consistent with the Mayor's Commission on Climate Change recommendations and allow sufficient time for the development community to adequately plan for the new mandate. And this slide has my contact information and a link to the project webpage. We're trying to get a shorter URL, but right now if you Google electrification of new construction, Sacramento, or maybe just Sacramento, electrification ordinance, you should find it fairly easily. Staff will be hosting more topic-focused outreach events like this one over the next month or so. Information regarding dates, times, and how to sign up will be posted on the Electrification of New Construction webpage. And if you're on our email list, you'll receive a courtesy notice. So now I'm going to turn it over to Stet Sanborn with the Smith Group, and he's our key speaker.
Thank you, Helen, and welcome everybody. As I get ready to share my screen, hopefully this comes up. Great, well, thank you Oh, I'm getting a little feedback. Anybody else?
Ellen, maybe if you mute.
Perfect. So I'll jump in. So today, in this webinar, we're going to be covering sort of some complex building types that we've got quite a bit of experience in electrifying, and sort of go through some of the challenges that we've seen, but also some of the technology that it's enabled the market shift in the last number of years. So primarily, I'm going to be focusing on laboratories, healthcare environments, and then a little bit on commercial kitchens. On the manufacturing side, I haven't seen any challenges yet from our manufacturing partners on electrification, but happy to take questions specifically on light and medium manufacturing when we get to the Q&A. For laboratories, really sort of talking about how we get over a lot of the high ventilation rates that are associated with labs, especially wet labs and chemistry labs. One of the big hiccups, which is along sterilization and equipment that might enable sterilization. And then specifically, the one area that actually provides a lot of the resistance on client sides that are looking at electrification in labs is actually benchtop equipment and sort of the love of the classic Bunsen burner. So I'll talk a little bit about the functions of that and what equipment we see sort of displacing that in all electric lab design. I'll also touch a little bit on hospital and healthcare environments and share some of our all-electric healthcare buildings that are ranging from mostly OSHPD 3 right now, but some that are in the works on sort of leaning towards OSHPD 1. And then I'll like I mentioned, I'll briefly talk about commercial kitchens and commissaries and some of the high throughput cooking strategies, but especially to provide some references for folks and resources that folks can go track down if they want detailed specific information about their particular cook line. And then at the very end, I'll just talk a little bit about resilience and backup as we see in these all electric buildings, because it's especially important for some of these challenging projects like laboratories. Just one intro slide. I know there's a Electrification 101, but I just have one slide to highlight the importance of our shift to all electric infrastructure, all electric buildings, is really in line with the state goals of decarbonization and a lot of local municipalities. But beyond that, when we start to look at the renewable makeup even today, we see between 35 and 40% renewable energy on the grid today right now. And when we think about the carbon emissions of our grid mix and our building types, it already makes sense today to electrify. So it's not a 2030, we should have electric buildings. Really, they make sense today from a carbon emission standpoint. And so a lot of our work on the engineering side has been to support our buildings where clients have been asking to make this transition now, in part to lower their carbon emissions. So the three things that I'll be talking about today is actually the biggest challenge is just overcoming business as usual, sort of standard approaches that have proven quite successful in project delivery for complex building types. These are the ones that are harder to change because the buildings themselves are usually more complex than commercial office buildings or schools, some of the first adopters of all electric design, but also because the facility staff who run the facilities and maintain them are very used to a certain type of building and building systems. So in healthcare or in labs, you have both the restrictions at the lab environment, whether it's a BSL sort of standard chemistry lab or all the way up to sort of BSL 3 and 4. There's certain types of equipment that have traditionally been gas-fired or gas-equipped, and seeing that equipment transition through takes some time and getting staff familiar with them. Hospitals are their own beast, in part because the varying demands within a healthcare environment, from ORs all the way to sterilization equipment and sort of autoclave situations. But the big challenge on those projects is actually their 24/7 schedule. These buildings are operating all day, every day. And so you don't have as much opportunity to put smaller systems in. You're looking at much larger sort of centralized equipment. So I'll talk a little bit about that. And then the image on the right is in commercial kitchens, there is still a love of flame. And in our projects that we're doing some large tech offices that are transitioning to all electric commissaries and all electric commercial kitchens, it's really about equipment swaps and reimagining how that cook line is delivering food, and sort of working both with the the chef, sort of executive chef, and walking them through what type of food cuisine are they serving, what is that delivery method, and what's the best equipment that can supply that. And oftentimes it's actually not gas. It's safer and healthier and actually sort of lower cost to deliver with all electric. So I'll talk a little bit about that. So the first project I'm going to sort of use as a way to explain some of the systems is a project that we're working on with affiliated engineers. It's at SF State, and it's their new science replacement building. So this is a building that is approximately half wet chemistry and half classroom. As you can see, it's a 5-story project. So again, from a height limit, it's a good sized project. And wet chemistry tends to be one of the more complex project types to electrify, especially because of the amount of air changes that are being driven by that hood exhaust. So wet chemistry tends to have higher levels of exhaust required in the labs through the hoods, and that air exchange means that we have to make up that air. For all the air that we remove from the building, we need to bring that same amount of air back in, and that can present quite a heating load or a demand for heating load. And traditionally, that's been provided by gas boilers that are heating a hydronic loop. On this particular project, what we're actually looking at is taking advantage of something else that occurs in a lot of labs. And this is not unique to labs, that actually happens at district energy plants as well, where you have a lot of heating and cooling that are actually happening at the same time. So if we think about all that outside air that we're bringing into a building to offset the hoods, there's still a lot of load inside the building that's requiring cooling. So in addition, a lot of these projects use a system called VAV with reheat to modulate air and deal with pressurization between labs and non-labs. That system, by default, tends to result in a lot of what we call simultaneous heating cooling. So we're heating and cooling things at the same time. Traditionally, we've had a boiler that was heating things, and we have a chiller and cooling towers that are cooling things. And you're doing both of those things at the same time. When we look at all electric buildings, we tend to be looking at what we call heat recovery heat pumps, or heat recovery chillers, or heat recovery heat pump chillers. And that piece of equipment is essentially taking the boiler and taking the chiller and getting rid of both of them and putting a new chiller in its place that can do both things simultaneously, so at the same time. So this piece of equipment looks at your heating demand and your cooling demand, and the waste from one becomes the other. And without going too much into how sort of heat pumps work, just know that a heat pump moves energy from one side to another. That's the simple description of what a heat pump is doing. So it takes heat, it removes it from the area that you're trying to cool, and it provides it to the circuits that you're trying to heat. Now, the nice thing about a heat recovery heat pump chiller or heat recovery heat pump, especially in the 6-pipe version, is that we also can go and grab excess energy from another source if we need it. If those two things aren't balanced perfectly, we can go somewhere else to grab that energy or to dump energy as we need to. In the case of a lab, a great place to grab energy from and push energy to is actually the exhaust airstream. So in this project, we're actually taking water source heat recovery heat pumps, and we've added a coil into the exhaust airstream. And so when we need extra heat, we can pull it from that air before it leaves the building, or in the chance that we're actually cooling dominated and we need to dump heat, we can actually dump excess heat into that exhaust airstream before it leaves the building, before it leaves the fume hood. This gives us a really great chance to cover the entirety of our heating and cooling loads with one set of equipment to simplify the design. But it also is taking advantage of energy resources that are already on site. So that exhaust airstream is a great source to pull heat from. It's a high value source. And so it's actually a very elegant solution, very simple. And the key thing from an energy efficiency standpoint is that heat pump chiller is doing two things at once for us. So instead of having two pieces of equipment, each doing something independently, we now have one piece of equipment that's doing two things simultaneously. And it's doing it at an extremely high efficiency. So when we talk about heat pump efficiency, we're generally talking about COP, a coefficient of performance. And we can see heat recovery chillers getting upwards. Let's say a typical heat pump might have a COP of 3, 3.2, 3.5 for a really good one. Heat recovery heat pumps, when you have simultaneous load, are typically seeing COPs greater than 7. So in that sort of 6 to 7, and depending on the richness of that source energy, you can get higher than that. So it's a really nice sort of simple and elegant way to deliver energy in a complex project. The next project I'll talk about is a Smith Group project that we're doing both the architecture and the engineering in-house. This is called Bioepic. It's at Lawrence Berkeley National Lab, and it should break ground in the next 2 months or so. And this is a biological research lab. So it has, it's quite complex. There are that lower floor is almost entire environmental control chambers that are simulating different climates around the world, doing research on climate responsive sort of biology. And the project also has a number of cryo-EMs, cryogenically cooled electron microscopes. So we have a huge demand for different conditions thermally in this building that aren't normally achieved by sort of traditional HVAC systems. And I'm not going to go, don't worry, I'm not going to dive in too far into the sort of piping schematic for this project, but just to show you that the same sort of systems, those water source heat pumps with heat recovery, are the same systems that we can actually use to provide all sorts of grades of energy to a project. So whether it's heating hot water, low temperature chilled water, medium temperature chilled water, medium temperature heating water, high temperature heating water, we're achieving all of those with heat pumps on site with this building. We're also using heat pumps on this project to provide both industrial hot water and domestic hot water. So the potable water that you would see at like a faucet, but also the industrial hot water serving experimental equipment. This project is also using heat recovery off of the exhaust fans. So again, that's a really important strategy for labs. Labs that see high air changes, that source of air that you're exhausting from the building is a phenomenal source to grab energy from, whether it's a traditional runaround loop as a heat recovery coil, or through a heat pump that's using it through more sort of active heat recovery. And for those of you who are like, oh great, those are projects that are in design, they haven't been deployed yet. Well, the building right next door at LBNL is the Integrated Genomics Lab. This is also a Smith Group project that we delivered. It is operational. Folks moved in, although now it's COVID, so less people are there. But this is a genomics lab. It's about half, a little over half lab to half office. But it's deploying the same sort of strategies. This one's actually using chilled beams for lab cooling because the air exchange rate isn't that high for a genomics lab. Certainly not as high as what we see in some of the more complex biological and chemistry labs. But it's using the same sort of strategies of using heat recovery off of that exhaust air, along with heat pump tied with in this case, a central plant that's all electric. So this project is operational, working, it's all electric. It does have gas coming to the building, but it's not hooked up to anything. It was more of a belt and suspenders, like what if, but currently it's not used for any of the benchtop equipment or HVAC systems. And that brings me to sort of one of the big things that when we're working with both, especially with college campuses on laboratories that are trying to go all electric, we hear a lot of resistance from faculty and staff around, well, what do I do without my Bunsen burner? Like this is like the thing that they want to know about. And I would say there's a couple of things that we do in lieu of a Bunsen burner. But the first one that I want to call out is actually the change in the type of laboratories that we see. More and more labs are moving towards large computational components. So far less of the lab work is done at traditional benchtops than we probably saw 15 years ago or 20 years ago, where a good number of the experiments are actually being done physically at benchtop environments. The reason that most of our labs, we start now seeing almost a 50-50 split between lab and office is because a good chunk of that work has actually moved to computational and theoretical modeling and computer-assisted experimentation. And so we see a pretty big reduction in the need for on-site Bunsen burners specifically, or other gas-fired equipment at the bench, at the experiment bench. But for those people who love the flame or want to understand what their alternatives are, there's a number of them, depending on what that flame was being used for. So there's two things primarily that the Bunsen burners were used for from an experimentation standpoint. One is sterilization, and actually that's probably the biggest one, is used for sterilizing equipment, whether it's loops or whether it's actual test tubes, sterilizing the equipment before it's used in the experiment, or for temperature control, obviously heating up something being used in an experiment. So there's a whole suite of equipment that's all electric or doesn't rely on central gas, and that's the key, is doesn't rely on a central gas supply that can provide that same sort of level of control or sterilization requirement. So I've shown a couple here above. There certainly are electric Bunsen burners, sort of quote unquote, that provide all the same function that a traditional Bunsen burner does. They sometimes can be limited in size, so depending on how big of a test tube or a flask that you're trying to heat, you may be limited in the selection of electric Bunsen burners. But for the majority of the time, the Bunsen burner is being used for sterilization. And so they have glass bead sterilizers as well as infrared sterilizers, depending on the type of equipment, that provide that same function. And then from a standpoint that more and more of our projects are going towards not all electric, we're seeing a number of projects actually provide isolated butane fired Bunsen burners. So there are products on the market within sort of the scientific world for portable Bunsen burners or sterilizers, depending on the need. And in lieu of bringing gas to a building and paying hundreds of thousands of dollars to bring gas to a building, connect it to the utility, distribute it throughout the building so that one scientist can use gas to heat a test tube, we're actually going through the science project with the team to actually say, okay, what do you really need? And do we actually need central gas to supply that? But there's a whole host of equipment out there that can provide the same functionality. So Smith Group certainly are not the only ones. We're not the only ones doing all electric labs. This project is actually one that was done by Bootman and Blavlit, who we partner with quite a bit. This is the San Francisco office of the chief medical examiner. So it bridges that gap between lab and healthcare. It's not so much healthcare as, I guess, death care, but sort of that same level of requirements from a lab standpoint. This project, similarly to the ones that we've worked on, uses a 4-pipe air source heat pump for both space heating and cooling. So it's a hydronic system. It can serve all the traditional equipment you typically see in a building that's hydronic. It's just using an air source heat pump with heat recovery. So it's a really great strategy of replacing 2 different systems with one that does both. And then you can still provide sort of the N+1 redundancy that you might have as a requirement on your project. So in healthcare environments, one of the big issues that we see is a lot of our campuses are actually legacy campuses. And the hardest thing on a large healthcare campus is actually working out how we're going to transition the project off of steam, because they typically all have either a high temperature hot water central plant or a steam plant that they've been relying on for years. And sometimes they're fond of it, sometimes they're not. But a lot of our strategies are how to phase a project off of steam. We can do medical office buildings sort of standalone. They're actually not complex at all, but it's the large scale healthcare environments, the sort of OSPOD 1 hospitals that typically have been tied to these sort of legacy central plants. And so getting new ones often means developing a plan to transition the project off of gas. There are still some systems though that I would say are still best served by a gas system. And typically that is around sterilization. So if they have a large throughput requirement for sterilization, it is hard to find a cost-effective steam generator that's all electric right now that serves high throughput sterilization requirements. And that goes the same for laboratories, especially ones that have vivariums. So if they're doing a lot of animal research, there's a huge load for sterilization. And we see that being quite a bit of a challenge to serve from an all-electric standpoint. So there's sort of the strategies that we see from electrification from these healthcare environments are sort of doing what you've always been doing, boilers and chillers, going to some improvement off of that, which is heat recovery, chillers, covering that simultaneous load, just like I showed in the labs, but then still having a boiler and chiller to make up the difference. And then trying to find some strategy to go all electric. And this is probably the biggest challenge for healthcare environments, is actually covering the total load outside of simultaneous heating and cooling, and whether that's an air source or a water source heat pump, or some other on-site generation to cover some of those non-electric loads. And the image on the left is actually one of my favorite pictures. It's from an affiliated engineers project at Stanford, their heat recovery central plant. So these systems are not limited to building level projects, but actually are quite applicable to even large-scale campuses. So Stanford made the switch for their sort of entire campus to going to this all-electric heat recovery central plant, and it has it's sort of future-proofed, adding the capability in the future to go to ground source heat sink as well. It's a beautiful plant. If you ever get a chance to go down there, it's a wonderful project that I just wanted to share. So the types of equipment that we see in these projects are just essentially bigger versions of what we see in smaller projects. So if you've worked on all-electric commercial buildings, or all-electric K-12 schools or higher ed buildings, you're probably already used to seeing 4-pipe air source heat pumps, 6-pipe water source heat pumps. These are all the types of equipment that we actually see in these complex buildings. We just typically have bigger versions of them, and or multiple versions, additional units to make up what we would call a modular central plant. So the technology is not radically different. It hasn't traditionally been used in this sort of in the lab environment. But I can share that from our experience, I think we have right now 5 labs that we're doing the architecture and engineering in out of San Francisco. All 5 of those labs are all electric. And 4 of them will have 0 gas going to them. So from a standpoint of that market shift, I would say 10 years ago, it was a one-off specialty project. If you think about some of the there's been a couple net zero energy labs. 5 years ago, 10 years ago, these were one-off projects. We're like, oh my gosh, I did an all-electric lab. I'd say for us right now, it is our general approach to labs. And then it's about finding if there's a particular part of that program that for some reason is impossible to fill with an all-electric source, then it's finding that very small impact gas appliance that needs to be. But I would say that from a lab planning standpoint and deployment of the labs that we're doing, we haven't yet found a case where we can't deploy that project as an all-electric project and avoid the gas infrastructure altogether. So here's a project that we have. It's a San Mateo County Wellness Center. So this is an OSHPD 3 clinic for the county health system in San Mateo. This project is just finishing construction and going out to bid. This will be, it's 3 stories, all electric health clinic, dental, primary care, and it will be net zero energy and has an on-site microgrid with battery for resiliency. So this is not pie in the sky. We're doing this also for projects that are sort of public bid, public budget, sort of not extravagant research labs with sort of infinite buckets of money. So we're doing this cost effectively today, even for the public sector. A couple projects, additional ones, the Wellness Center in Cloverdale, California. Again, this is a sort of primary care facility that Gutman and Blauvelt did. And this is an all-electric healthcare building. And then the one in the bottom, this was the Kaiser Medical Office building in Santa Rosa, and this is one done by Integral Group, were the engineers on this project. And that one's all-electric, no gas to the building, and done with sort of rooftop package units. So very sort of straightforward design, just heat pump based. So again, not radically different. So as I'm just going to touch really quickly on commercial kitchens, and then resiliency, and then we'll open it up for Q&A. For the commercial kitchens, I would say your best resource for your particular cook line is to reach out to the folks at Fishnick, Frontier Energy at the Commercial Food Service Research Center in San Ramon. They have a phenomenal depth of research and tested equipment for every sort of delivery of food you can imagine. And they consult on almost all of our projects that we do commercial kitchens on for not only going all electric, but also just flat out increasing efficiency. It's a phenomenal research, so I would point anyone there, they're fantastic. And what it comes down to is actually often talking about the cook line, the delivery of the food, but also what type of equipment is needed to actually deliver the kind of food that you want. So in the image on the left, you'll actually see an induction cooktop. So this is a commercial induction range. Right here, you'll notice no open flame equipment right here below the hood, and then an electric sear griller to get the char marks that everybody seems to love and expect often for certain types of food. In the upper right-hand image, this is all electric induction-based wok cooking. So we hear a lot from folks who are like, oh, well, you can't get this. I can't get away from my classic wok for Asian cooking. Like, yes, they have induction versions for wok cooking as well. And then I'd point out that a lot of the food delivery has changed quite a bit. So the image in the lower right is a commercial version of a sous vide machine. A lot of food prep now is happening in sous vide style, where it's being actually prepped ahead of time and held at an optimum temperature, and then finished right at the end before it's delivered to the customer. And almost all that equipment is already all electric. So just my last couple of slides before we open it up to questions is we always get the question about resilience when we are being asked to do an all-electric building or when we propose one, especially because of the preemptive power shutoffs across California as a response to wildfires. The question is, well, why do I want to go to an all-electric building if you're going to cut off my electricity? I'd rather have it all be on gas. And the honest answer is, well, even when your system is on gas, almost everything that moves that energy around your building is still electric, whether it's fans or pumps. And so there still is a need for resiliency on the electric side, even if you are connected to gas. And so my question always is, well, do I want to try to harden or make two systems resilient, or focus my attention on making one system really resilient? And so in the case of, this is a healthcare project that we actually are working on a microgrid right now, coming up with the sort of daily energy profile, we can match that to a PV and battery system. And I wanted to share just the economics because everybody asks me, like, well, does this make sense financially? You know, when we do full life cycle cost analysis for all electric solutions, we're taking into account the cost of energy, we're taking into account maintenance, life of batteries, life of PV systems, all of it, grid demand charge manipulation, all of it. And so on our last project that we're working on right now for an administrative building on a healthcare campus, we're looking at 4-day resilience of PV plus battery. So the PVs can recharge the batteries during the day, along with covering the load. And that combined system, although big, it's a lot of stuff, we're able to deliver that project even with contractor costs. So these are not costs that I've made up. When we look at a levelized cost of energy, we're getting that client down to below 10 cents a kilowatt hour in California. And this is a nonprofit client that can't take advantage of demand of accelerated depreciation or some of the other investment tools. But we have the ability to do cost-effective, resilient solutions now with PV and battery and all-electric design. And so I would just put it out there that it's not totally crazy, even in today's economic model. It's more of a space constraint of, do you have the space for the technology in your project? So with that, I wanted to open it up to questions and make sure I didn't run too far over, Helen, and hand it over to you guys.
This is Jennifer Venema with the city. Fantastic presentation. We'll just acknowledge and apologize. We've got some wires crossed. I know a few folks were stuck in Zoom limbo land, so really want to apologize there. Thank everyone for their patience. And it was great that you did go longer, Stet, because folks could catch a little more. So perhaps if people had any questions on Stet's presentation, he had some great case studies. I also want to note that we've recorded this and we'll send a link to everyone registered in addition to posting it on the website.
Okay. Well, are there any questions? Or we also have Steve Oliver here. He can talk about SMUD incentives if you want to hear that. I don't know whether that's kind of the same SMUD incentives on the commercial webinar that we already did. But let's just find out Are there any burning questions that anyone has? Or shall we move on to SMUD incentives? Go ahead and put it in the chat or unmute yourself, one or the other.
And I'm happy to answer questions either through the chat or even after the presentation if folks email me.
Hello, this is Tom Cabot. I appreciate your showing the cooking equipment. I was wondering if the facility has produced a kind of a side-by-side stack of gas equivalent and the electric equivalent, because in going to some cities' reach code hearings, occasionally city council members are restaurateurs and they are adamant about knowing that nothing can ever keep up with their dirty old burner. And so I was wondering if you have
so Fishnick actually has a couple side-by-side comparisons, sort of like line or cook item by cook item, and they also have, as part of that, they have sort of cost, both initial cost and cost to operate, and so they've shared that information out, and it's actually kind of great. It's hard because for some items, the cost delta between the gas version and the electric is quite different, because we don't have the market penetration for some of the items. But for almost every cooking style or cooking in product, they show an all-electric version that you wouldn't be able to distinguish at the end of the cook line. That being said, their biggest focus is on making in lieu of just doing a one-for-one swap out of your kitchen and how you've cooked before, is actually working with you to see if that's the most efficient way to deliver the food, which is actually, if you talk to restaurateurs, their margins are not amazing. And finding actually a lot less costly ways to deliver high quality food is, at the end of the day, often what they're more interested in. And so rather than just, because I can almost tell you if you do a one-for-one equipment swap, it'll cost more on day one. The first cost will almost always be higher if you try to emulate exactly what you have with an all-electric version. But the real genius of the work that they do, and they're a utility surcharge supported entity, so they support projects in California for the public. The real genius of what they do is actually help you with your food delivery and say, well, in lieu of this piece plus this piece plus this piece, have you thought about just doing this? It's a turbo oven. It does 4 of the things that you just asked me to do, and it will do it as one piece of equipment and more efficiently. Or if you do this swap plus this swap, your hood size can actually shrink because now your cook line is actually smaller. And for all of us that are in the sort of efficiency and MEP world know, the smaller that hood is, the less air we have to move through that kitchen. And there's a huge energy benefit to making that hood as small as reasonable for your cooking needs. The other piece that I would add is that a lot of these all-electric options, especially the induction cook lines, have much less heat loss around the cooking device. A much higher amount of the heat is actually delivered to the food, and that results in lower kitchen temperatures. And so there's definitely a comfort side as well as a safety side for a lot of these swaps, where there's less open flame, there's less residual heat dispersed to the space, and so we have to spend less energy trying to cool the kitchen to keep staff comfortable while they're cooking. So there's kind of a multi-pronged benefit when we look at all electric kitchens. But if you try to do a one-for-one swap without thinking about anything else, it's likely going to cost more.
Yep. I think that's great advice. It goes along the lines that Amory Lovins often puts forward, and he attributes an interesting quote to Dwight Eisenhower about, if a problem seems too hard to fix, expand the problem. And so look beyond the little one pot for the other pot swap, look to the whole cook line.
Yeah. There's some amazing technology right now that's been coming to the market, especially in the programmable equipment, where you can program in the food menu and the sort of cooking instructions for pieces of equipment that can do almost the whole process together. And so there's actually a lot of innovation in the cooking space right now, and almost all that innovation is around all electric kitchens.
So I have one more question about labs, and I'm sorry I joined a bit late, so I missed the early part of your discussion. But I know over here in Menlo Park, we had one of the first exemptions in a REACH code for labs, unfortunately caused by a single politically powerful developer of bioscience labs. And we, as an early mover, we couldn't, we chose not to fight him. We chose to make an exemption process. But the thing he needed, he felt the need for an exemption about was the large makeup air requirement. He would never want a dirty open flame anywhere in his biolabs, but they do need a lot of air. And so his worry was that during a wintertime power outage, when equipment is being powered by on-site diesel generators with a limited fuel tank and disrupted roads, that they might run out of fuel if they were also heat pumping the building conditioning to try to keep the lab from descending below a bottom temperature. Now, this wouldn't help him in the summer when temperatures are high, but you know, his whole worry is
no
about
gas for 3 weeks.
right. His whole worry is about this winter event, which I think can be partially addressed with heat recovery ventilation.
Yep.
As just a method to try to get at his root issue, which is not letting the lab temperatures drop too low in our severe Menlo Park climate, where it once in a while gets down to 35.
Yeah, I do enjoy the conversations where our clients locally here are like, oh, it's so cold, this is going to cause a horrible problem. But yet we're doing these same strategies in Chicago and the upper Midwest that actually have winter. And so you're right, the heat recovery strategies are actually one of the best strategies to bump up that incoming air temperature in the winter event. One, so that the actual heat pump is doing less work. But as I showed, and you might have missed it, the strategy that we like the best is actually using the exhaust airstream as our source of heat with a heat pump. So adding a coil to the exhaust airstream plenum, where we can actually extract all this valuable energy that we're extracting out, and actually more than we can with like a simple runaround coil. We can actually pull a lot of heat out of that exhaust air relatively easily and at sort of low energy demand to do that. It's a really good heat source, is the exhaust airstream. And so we haven't run into a problem yet where we've had a project, and like everything on our complex labs, especially we do a lot of work for the DOE and sort of national labs. We have N+1 for everything. These experiments need to continue regardless of what's happening out in the world, both from a safety standpoint and for a number of these experiments are going on for our multi-month experiments that can't be interrupted. And so resiliency is a huge issue. Our projects up at LBNL, our 2 all-electric labs up there, have a really large central generator, actually 2 of them, because there's backup for the generator. And the fuel supply is set up to essentially run for them, sort of worst case, they're expecting, I think it's 5 days for them that they would expect to have no resources to be able to get to the site. But it's a project by project basis. On our projects now, we're seeing a much bigger drive towards diesel backup plus battery plus PV, and using the PV and battery to cover normal power loads and the backup generator just to cover the emergency loads in those situations, so that we can actually get a project to run for multiple days, 5 days, 6 days, 7 days, almost in perpetuity, because a good chunk of that load is actually being powered by PV and battery, which is recharging every day for the most part. So yeah, resiliency is a really important issue, but I would hardly say that it requires an exemption to be for being all electric. Because if you're looking at gas-fired generators, the reality is in coastal California that when we have an earthquake, gas goes down for a month, and it takes that long to bring that infrastructure back on. And so what do you do then if you don't have access to gas, you don't have a diesel backup, and you have a large gas load in your building? Then your experiment fails.
We're gonna take a I guess go back to our second speaker. We have Steve Oliver here from Smud to go over Smud incentives, and then if there's time left over, we can take additional questions. So I'm going to turn it over to Steve.
Thanks, Ellen. We'll power through this real quick to leave some more time for questions. Just wanted to give a quick overview on Smud's programs and focus on the ones that are most beneficial for new construction. So we're currently doing both energy efficiency and electrification programs. We have a range of programs ranging from express energy solutions, that's your deemed savings sort of menu where you pick a rebate. If you had something large and complicated, retrofit, we would use our custom program. For small and mid-sized business, we actually have a turnkey program that'll do everything from the audit to pick equipment and help with the project management. That's called Complete Energy Solutions. And generally for new construction, we use a program called Integrated Design Solutions, and that's our formerly Savings by Design program. And that's for new construction or extensive building remodels. And then we have two multifamily programs. We've got the multifamily all-electric smart home program, and we've also got a multifamily retrofit program. We offer programs for green pricing. This is very beneficial to all-electric designs because if you purchase Greenergy, which is our entirely carbon-free supply, then you can claim your site as a carbon-free energy consumer. And then Neighborhood Solar shares a fairly new product we have, and that's to help residential customers that have challenging situations, helps them satisfy the PV requirements. We do a lot of incentives and rebates for electric vehicles. We can incent the vehicles themselves, battery electric vehicles, anything from passenger cars, this is for commercial, up to Class 8 heavy trucks and buses. And then we can also help with incentives for the charging infrastructure as well. Most of these incentives are done through a partnership with Cali VIP. And those incentives are $6,500 for a level 2 charger and up to $80,000 for a DC fast charger. A really interesting program for new construction is our Power Direct, which is called an automated demand response program. This is where we would work with a building owner to come up with a strategy to have the building go into a low power mode at a signal from Smud. And that low power mode would be called during periods where we're buying carbon intensive electricity or very expensive electricity. We might ask our portfolio participants to shed load. And it's all with measures that they've agreed to. It's voluntary. And in exchange for their participation, we pay them an incentive, a recurring incentive for shedding load. But we can also pay a one-time incentive to help them interconnect with Smud and set up the enabling technologies. The heavy hitter in new construction is our Integrated Design Solutions program. It used to be called Savings by Design. There's two paths for integrated design. One is a calculated approach where we will look at the energy that's saved by using energy models and base the incentive on that. We're paying incentives up to $150,000 for electrification and up to $100,000 for energy efficiency. And any design team that completes an all-electric building, there's a stipend of up to $10,000. And then for smaller buildings that don't have that are sort of your more day-to-day buildings, we also have a menu approach where you would just pick from a menu, heat pump technology for water heating and heat pump technology for space heating, induction cooktops, kitchen equipment. There's a menu, and pick from that menu for incentives up to $150,000. And then we have a multifamily Go Electric Smart Home. It's a pretty simple program. If you don't bring gas to the site, each dwelling unit receives an incentive of $1,250, and then any of those units that upgrade to an induction stove will receive an additional $500 rebate. And we also have a program for multifamily retrofit and electrification as well. And then The program manager is most commonly responsible for these electrification programs. Ryan Hammond manages the commercial new construction program. Raina Langen manages the smart home, Go Electric Smart Home program, which includes multifamily. And then I'm the building electrification lead for the commercial delivery. That's your quick overview. If you have any questions for Stead or me, I'll be available.
Thank you, Steve. Are there any questions about the SMUD programs? That sounded like feedback to me. Okay, so let's go ahead and open it up to questions about everything. And I know there will be more questions for Stead, I'm sure. No more questions? You can put it in the chat or you can unmute yourself.
One question did come up in the chat that was just sent privately, but it was looking for the resource for the kitchen equipment sort of comparison. So I will see if I can find that. If not, I can reach out to Mark at Fishnick and might be able to get that. So if I can't find it before we end, I can share it with you guys to send out to participants.
Helen or Jennifer, it may be good to use a little bit of this time, at least to talk about upcoming webinars.
You're on mute, Helen.
Wasn't actually prepared to talk about it. We have, let me get my calendar open. I don't have it at the top of my head.
While Helen's doing that, I can just add as well as recap for folks. I think this reiterates points Helen made at the start of the webinar when many folks were on the meeting. Just a reminder that what the city's working on right now is an ordinance to electrify new construction, which would be effective in 2023 for low rise and 2026 for high rise, but really looking at how we onboard and support this sooner rather than later. So we do have a number of webinars that are occurring, I think maybe 2 or 3 through the end of the year, and at least 2 we're trying to schedule in early January to late January, including one on restaurants and commercial cooking. So that might be when we invite Stet to join us at again and reaching out to some other folks. So it will be an ongoing topic of discussion, but just a reminder that we're really focused on the transition of new buildings while thinking more broadly about retrofits to existing construction, replacement of appliances on a longer term time frame.
And if we wait a minute or two, I'm uploading a PDF of the presentation into the chat window. So as soon as that lands, it's available to you as well.
Oh, that's great. Helen,
Tom, did you have another question?
I'll add that.
Yes,
Oh, I'm sorry, Tom, I'll just finish my thought quickly that we'll put a link in the chat to the city website right under Stet's using PowerPoint. So we do have a list of meetings there, and Helen, specific dates, I think our next meeting, do we have any more for December?
We don't have any more that are, we have some tentative dates, and I say tentative because we've kind of identified the dates and we have to sort of flesh out everything, but it looks like we're going to be doing one on workforce and electrification on January 15th. This one is also at noon. And we're looking at probably January 25th, also at noon, for one with restaurants, specifically for restaurants.
And we have one coming up for low income development.
Oh, yeah, right.
Is it the 9th?
It's the 7th, I think.
The 7th, okay.
Yeah, I think it's the
Yeah.
7th. Let me just double check that. I don't want to tell people wrong. I already somehow got the link mixed up or something. I don't know what happened today. Yeah, that is the 7th at
3 o'clock.
3 o'clock, and that one is part. It's like during a housing policy working group. It's like we're taking half of their meeting, and so and so that one will be about affordable housing and multifamily housing and everything. So
I'll just note to folks, we do have email signups on the webpage link I provided, and as part of our follow-up, we will be sharing these resources and can summarize the upcoming meetings as well.
okay, so unless you have another question?
Tom had a question. I'm sorry, Tom, I completely
I
interrupted.
had a quick question for Steve based on something Jennifer mentioned. So Jennifer mentioned Sacramento's what I think of as a very slow rollout of commercial all-electric requirement. So there will be many years of buildings being planned while they're allowed to use gas. And then I like the incentive that Smud is offering of, I think it's $10,000 to design teams to incent them into making all electric designs or proposing that to their clients. And I'm wondering, does it make sense to have a much bigger incentive for the first project per firm, and then a smaller one for the next project per engineering firm, and smaller, just to get them over the hump? Because I have this feeling from what I've heard about engineering contracting firms that they can learn, but they don't like to.
Yeah, we've kicked that one around quite a bit. For those who remember the Savings by Design program, that's where the design team incentive came from 15 years ago. And it was pretty lucrative. You could get $50,000. And our experience over the years has been that the design teams that are already efficiency minded and electrification minded, they're already doing it. And the $50,000 wasn't enough to kick them to a different school of thought. So what we were hoping to do is sweep up the ones that were doing, say, small projects and had to do a little extra work or a little extra design or a little extra modeling to demonstrate it. And those were the ones we were hoping to incent with the design stipend. The way it's calculated is you get that $10,000 pretty quick. So that could be a relatively small job compared to the old design team incentive, which required a really high standard and a lot of sort of administrative work. But yeah, no, we considered that option as well. And I think the budget we've got, we decided that the ones that weren't already full speed ahead on electrification were the ones that we wanted to have a really simple stipend to hopefully offset some of the additional work.
All right, thank you.
Sure. Yeah.
Right.
Yeah.
So with that, okay.
I do have another question for Stet, actually, building on some of Tom's comments. Just curious if you could talk to us a little bit with special uses such as big labs or healthcare facilities. What would it mean for a facility like that going in, say, to be constructed in 2023, 2024, that isn't all electric, but is required to include electric readiness? So how much of a cost or a burden, what does that mean for additional electrical capacity? Would love
Yeah. So it's it would definitely be a little bit more complex for those projects. And it depends on what systems they're including in the base building. So if it's really trying to replace, say, a boiler, conceptually, if the project already has a significant air conditioning load, in other words, a big set of chillers that are providing cooling, to swap those out for heat recovery chillers doesn't have a significant electrical demand increase to offset some of the heating load. It's if you're trying to offset the entire heating load in the future, there may be some additional equipment that you would need to plan for, but it shouldn't be. If you already have a significant cooling lab, and cooling load, and most of these projects already do. Healthcare projects, labs, they have significant cooling. They have a lot of equipment, a lot of internal loads. It shouldn't be a deal breaker to plan for that additional capacity. The risk is if you say, take a boiler and literally just replace it with an air source heat pump, and there's a chiller right next door that's providing cooling. And so now you have two pieces of equipment, one for heating, one for cooling. Well, that's where you're going to add significant amount of load. But if you actually approach the project from a heat recovery standpoint and say, well, or add a little bit of thermal storage, then you can dramatically reduce that sort of peak electrical demand on the project. But I would say, like for offices, even if you're all electric ready and you already have air conditioning, you should be able to do it with a heat pump and provide heating and cooling without a huge electrical demand increase. But it's every time you say, I want to do a one-for-one swap with one piece of equipment and take a boiler and turn it into a heat pump, then it's a huge load and it's a huge space impact. But if you rethink the way that your plant is set up, then it doesn't have to be that significant.
That's very helpful, Stet. Thank you so much.
Yeah.
All right. So thank you, Stet and Steve, again, and everyone for joining us and lending us your expertise in electrification. And I guess we'll see everyone next time. Thank you.
Thanks, everyone.
Have a nice day.
Thank you, everyone.